computer. Cool. All right. Well, thank you all for coming to this another workshop hosted by Quantum Computing at Davis. I think in our last sessions, I talked about how ion-trapped quantum computing works, and that was sort of a whirlwind tour of all the underlying physics and all the stuff that goes on sort of behind the doors. So what I want to talk about today, though, is we're going to transition back to algorithms, and this won't be as formidable as when I was talking about the quantum Fourier transform. That's like a two-part workshop, and even I, still see some parts that could definitely be improved. But today is sort of like I would argue, a gentler day. We're going to be looking at what I call black box algorithms. So without further ado, let me go ahead and share my screen here. And now for this particular workshop, I do intend. Oh, whoops! Here we go. There we go. Okay, cool. I have to rearrange all this Zoom stuff, and I'll have the chat open. So if there are any questions or any people who have just come in, you're more than welcome to ask your questions, say hi, and so on and so forth. So the idea behind black box algorithms, you see these a lot in quantum computing. A lot of algorithms do this, and it's basically you have some function. There will be some function here. If there are any like AV issues, feel free to speak up as well. I'll try and resolve it as soon as possible. You have some kind of function. Normally we just call this the black box, and you make some number of queries to try and get an answer out of it. And we can do this classically. I mean, this isn't anything new. I mean, this is at the core of a lot of traditional computation. But the thing with black box algorithms in quantum computing is the goal is that you want to be able to get your answer with the least number of queries possible. That is what we would like to see as the speed up, as we like to call it in computer science or a standard parlance. But the basic idea is that with normal computation, there's kind of like an upper bound to how many questions you have to ask or query the black box to get an answer. But with quantum computers, we can actually speed this process up dramatically, exponentially in the best case. In fact, I'm going to show you one of the very first instances where this was sort of proven. And this is where I want to talk about and it has a very cool and fancy name, the I think this is pronounced Jozza. If anyone has like a correct pronunciation, feel free to hop in. So this is known as the Deutsch-Jozsa algorithm. And this is normally taught as sort of a very, very introductory algorithm. But I bring it up because I mentioned it earlier before the recording started. A lot of the existing explanations play a little fast and loose with the mathematical notation and what's actually going on behind doors. So that's what I wanted to try and cover today. So normally, with all algorithms, there is a problem that we are trying to solve in a deterministic and fast, in an efficient manner. And Deutsch-Jozsa's this problem itself doesn't really have any actual practical usage, but it's one of the earliest examples of showing how quantum computers can be drastically faster than classical computers. And the question goes something like this. So I'm going to give you a function. I'll give you this function here. And it will have some binary string that it takes as input. And the function will take, so this can be any arbitrary length input. So that's why I have to have the n here. So it could be 1 bit, it could be 10 bits, or 64 or 128 bits. But the output is only going to be a singular bit. It's going to be either 0 or 1 for any of your inputs. Furthermore, I'm going to give you a restriction that says that your function is going to be classified as either balanced, or it can either be what we know as constant, balanced or constant. And what this really means is if the function is balanced, that means that half of the inputs will, or half the output will either be zeros, and the other half will be ones. So one half of your outputs are going to be zeros, and the other half are going to be ones. So that's what we mean by a balanced function. Whereas a constant function, we're going to have the restriction that all the outputs of the function, regardless of the input, are going to be either 1 or they're going to be either 0 for all the inputs. That's what we mean by a balanced and a constant function. And I think you can already tell this isn't a very useful problem to solve. I can't think of any particular instances where this problem is explicitly useful. But it's a toy problem. It really is a toy problem. But it really highlights some of the useful tools or components that get used in other more advanced algorithms, like Grover's algorithm, which I eventually hope to work towards. So this being said, before we jump into the quantum realm, let's try and figure out what the classical performance is. So our classical performance. And what do I mean by performance? Well, I mean how many inputs, how many times do I have to evaluate f to get, here, so I just put the number of times to eval f to, let's see, figure out if balanced, I'll just do balanced, or bal for shorthand, balanced or constant. How many times do I have to run or execute our function in question to figure out if it's balanced or constant? Classically, even with any traditional computer, not non-quantum, we have to evaluate one input at a time. And the actual upper bound that you're going to get is 2n to the minus 1 plus 1. And this is straight off Wikipedia. And then you're thinking, Wikipedia is usually something that most people tell you to avoid. But this is actually very easy to verify. And the reason being is, let's imagine that our function only takes, say, 2 bits of input. So that n, the n right here is sort of the number of bits for the f of x input. And I'm trying to keep things short and sweet here, so I'm going to say that, okay, n is just equal to 2 bits. So our function only takes 2 bits, which means that the inputs are either going to be 0, 1, 2, or 3. 0, 1, 2, or 3. Now, if I want to figure out, let's say if it's balanced or the worst case scenario I'm going to have to do. So if I plug in 2 for here, so that means 2 to the power of 2 minus 1. That's just 2 to the 1 plus 1. So that's just 2 plus 1, which equals 3. So in the worst case scenario, I will have to run the function 3 times to figure out if it's balanced or constant. And the way I can sort of display this is, okay, let's say the first time I might evaluate with 0, 0, the output becomes 0, right? And let's say maybe I evaluate 0, 1, and the output is 0. Now, if we run just 2, we're still not certain yet if it's balanced or constant, because if it's balanced, I mean, that still means that the other remaining 2 inputs could give 1 or 1. But if it's constant, that means it could either be 0, 0. So as a result, we have to run it one more time just to figure out. This is kind of the tiebreaker, and this is what's going to tell us. Okay, that means it's either balanced or constant. So you can see the worst case scenario. It's 3 inputs in here. Now, just for thoroughness, not a lot of computer scientists like to focus on the best case scenario, but the best case here is actually you only have to run this twice, because there's the chance that you could get a 0 the first time you run the function with, say, 0, 0, but then the next time you run it, you get a 1 for the next time you run it with, say, the input of 1. And you'll find out that, hey, this can't be constant because you have non-matching values. In which case, now we've immediately deduced that this has to be a balanced function. And it can't be like some other wacky function, because going back, I just gave you the restriction that your function can only be one of 2. It can either be balanced or it can either be constant. There is no in between. So therein lies the classical sort of worst case bound, which is this formula right here, 2 to the n minus 1 plus 1. Now, for quantum, the quantum performance, this is the real super cool part. So the quantum performance, this is very exciting. Doesn't even need an n. It just needs 1 evaluation of f of x, regardless of how big f of x is. I only have to run this algorithm once, and I can tell you if it's balanced or constant. And this is sort of once again, I know I've said this like 2 times now, but this is the earliest case where there is proof of the potential for quantum speedup. And once again, it's a toy problem, so it's not really useful other than a piece of proof. But the reason it's still worth going over is because a lot of the principles behind its operation get reused in more advanced algorithms. So for quantum performance, we only need 1 eval of f of x. So this is the really exciting part. Now, let's try, and I'm going to actually go ahead and maybe start explaining this backwards by drawing the circuit first, and then I'll kind of dissect it from there. Before I go any further, are there any questions from what I've just explained in terms of the balance versus constant functions, the classical performance, and the quantum performance? Any questions so far? Or no?
I have a question.
Go ahead.
So I know how relevant it would be, but how would you account for recursive problems where you're not sure when it will resolve?
That's interesting. So what exactly do you mean, like if I were to define f of x in like a recursive fashion and there might have been some kind of like delay that I'm uncertain of? Is that what you're getting at? Or
Um, I, I, I can't recall the exact problem, but basically, if you have a function that doesn't resolve, or you don't know when it would resolve because it's recursive, how would that? Oh, how would you contextualize that within this problem?
so I don't think this problem permits recursive. So Mark, do you know a thing or two about this? I've never thought about a recursive. I know there's like a recursive Bernstein-Vazirani instance, but I don't think you can have like a recursive instance for this particular function. I mean, we just assume like this function is the black box, and the moment you push something through, you will get something out. So I'm not too certain.
Okay, maybe. All right. So how about this? The result of a function is uncertain in its completeness, insofar as you don't know when the function completes its calculation.
Oh, you mean the amount of time it takes for the function to run?
No, not just the time. It's also like you don't know uh, how much. I mean, it's kind of silly to say this, but the volume of the uh, result that you get from the function, if that makes sense.
I
Because
I think I know what you're getting at, Jithan. Like actually you would, because you would still know like that using certain amount of quantum bits and then sampling across them, you will get X amount of basis states. You'll get a certain amount of 0 and 1 states for each quantum bit that you have. So kind of what the responses will be. As for recursiveness, that, to be honest, like that is something that could exist in quantum devices and quantum algorithms in the future. I was just reading yesterday about how on the IBM like simulator, you can put like if statements that'll actually like look at, like there'll be like if statements on the quantum bits themselves based on their states. And so technically based on that, you could have some sort of a recursive state that continually checks until it gets some sort of measurement out of it that you would want. But in terms of most current hardware today, including IBM's, there is no ability to even really do a recursive step, because you're essentially only able to send a certain number of hardware specific steps and then only get out those certain number of basis states. So those two things are always going to occur with any of the quantum computations that you do. Does that kind of make sense?
Yeah, it does. This is also partly because I remember reading about recursive quantum bits years ago. I think it was like a Japanese paper. So basically, one quantum bit through a form of like cyclical recursion. Because I know it's kind of separate to what you're talking about now, but that's where my doubt comes from. Because basically, they kind of theorized, and I'm not sure about the proof, that like with one quantum bit you can kind of, how do you say, you recursively use it as multiple quantum bits. So they showed that it's possible to have about 90 to 100 quantum bits by through recursion of one quantum bit, if that makes sense.
That's interesting. If you manage to find the link to that paper, I'd be very inclined to, because I'm totally alien to I've never heard this before until now. That is very interesting. So I don't quite know what it bodes for Deutsch-Jozsa exactly, but I'm just thinking of f of x in terms of a very sort of simple, direct function.
Fair enough. Fair enough. Sorry, I'd like you to continue. It's really interesting.
No, I mean, it's what you brought up is a good point, though. The nature of f of x, but that's also one of the reasons why a lot of these algorithms are just called black box, or I use the term black box on them because the way they're designed is that you should not exactly know how f of x works on the inside, or you just shouldn't have to be worried about that at all. You only have to worry about the quantum inputs and the outputs. So with that being said, I will go ahead and resume. And I want to point out something that is somewhat problematic with how I am, we have to get f of x into something that the quantum computer likes. And right now, the quantum computer does not like f of x. And let me go back to the definition here, and you'll see why soon enough. So I mentioned you can take any arbitrary number of bits for the input, and then on the output, I guarantee you that only a singular bit can come out. But this operation by itself is not reversible, meaning that if some output comes out, like if I give you a single value, like a 1 or a 0, you can't really sort of go back and figure what the inputs were. And this reversibility is pretty crucial in quantum computing. The vast majority of gates are supposed to be reversible, and that's sort of that follows in with the property of a gate having to be unitary in quantum mechanics. And this idea of unitarity goes beyond quantum computing. This is very fundamental to quantum mechanics. And I think in my prior workshops, I have explained what a unitary matrix is, and it has a number of very special properties. But reversibility is definitely related to it, and it has to be present. And so what's going to happen to f of x is in the circuit, I'm actually going to rephrase how exactly f of x works. So if basically you're going to have a component in your circuit that looks like this. And I'm going to explain this soon enough. So it's unitary, and we notice that nothing really happens to x here, but then something interesting happens here, modulo 2 f of x. So now you'll notice that this u just means this is unitary. So given the outputs, I could go backwards and get these inputs here. And we're performing the following mapping here. So given x, y, we're just doing this map to x, and then we're doing this map here. So we're just mapping the inputs to the outputs. And the thing that I want you to note here is that x is the input that's getting evaluated, and then y is kind of this ancillary qubit that is going to become very useful. And it doesn't look like it's useful now, but I will explain it near the end. And to prove that this is reversible, usually what I'm going to do is I'm actually going to reevaluate. So this is one application of u of f, and this gives you this. Now, what happens if I apply u of f again? What actually happens is this. So x, nothing happens to x, but this happens. F of x, and by the way, I should mention this is this wonderful explanation of like why the gate has to be this way, or why you have to embed your function into this sort of quantum black box comes from, let's see, Sevag Gharibian. So he has a series of Intro to Quantum Computing. It's from the summer 2018 master's level lecture at the university he works for, which I'm embarrassed to say I don't quite remember off the top of my head or in my notes. But basically, I should mention that this is the exclusive or if you want to be very fancy, so if you want to drink your tea with your pinky up, you can say that this is 2-bit, or this is addition modulo 2. It basically is just binary addition. And whenever you have an exclusive OR of the same thing, so if you had like 1 XOR 1 or 0 XOR 0, these always evaluate to 0. So basically, this goes to 0, and as a result, you are left with x. Nothing happens to your x input, but your y input does become y XOR 0, or anything XOR with 0 essentially stays the same. So it's just x. So I've just proven the reversibility of this, and you need to embed that f of x in this format to get it to work in the context of the algorithm. And don't worry about. I should be a little more careful here. This could be an individual qubit. but more often than not, it could be multiple qubits. But y is always guaranteed to be a singular kind of ancillary qubit that gets fed in. And there will be some, we're going to take advantage of the relative and global phases to figure out whether or not this function is balanced or not balanced. But by doing this, we've made it unitary. We've made the function unitary, and the quantum computer is more than happy to use this in a larger circuit. So this is just part of the circuit. Let me draw the whole thing out for you. In fact, so we're going to start. Let's see here. Shoot, hold on. My desk here is a little messy. I have a well, my desk is set up. I have like a workbench here, with like some voltmeters and parts strewn over it. So I have my notes on like half that desk, but I digress. So I'm just going to draw out the whole circuit for you, and we're going to have 0 for this input. And this could be any number of zeros, I should mention. And this is, so usually we put this like slash and an n to denote like, okay, you can have an n number of qubits. And n number of qubits is the exact same n that I'm talking about in the worst case performance here to the n minus 1. It's the number of bits for f of x as input. So we have 0, and then we have 1 here as an input, and this is only a singular qubit. This is only 1 qubit. So regardless of how big n gets, you only need 1 qubit. We apply some Hadamard's here, and then we get to the function here, u sub f. And then we're going to apply the Hadamard yet again, or actually, hold on. This is normally when we have multiple qubits, we're going to do this. If you're not familiar with this notation, don't sweat it. I will explain all of the notation to a T, because I mean, math is very nice for compactifying expressions, but when you're learning, you really do want to take the time to sit down and expand the stuff you're seeing. And this qubit, okay, this qubit so this is pretty interesting. Once this singular qubit goes to the function, it essentially becomes kind of useless. Like in the math, you actually drop this qubit after you've evaluated it. After you've evaluated it, though. But this, in the beginning, it is very crucial you have this ancillary qubit. So I'm going to split up my explanation into a series of steps. I'll start something like this. Cool. So this is so there's essentially 1, 2, 3, about 4 to 5 steps that go on here. So we'll start with step 1. We want to prepare. Oh, whoops. So for step 1, we want to prepare the initial quantum state, and normally your initial quantum state is going to look something like this: ket 0, and then there's a circle with an x in it, an n, and then 1. So what the dickens does this mean? Basically, this n is just the number of qubits, and we're saying we want n qubits that start in the sort of ket 0 state. And this symbol here, the circle with an x, that's the tensor product or the Kronecker product. I mean, I think one is the more specific application of the other. There's a very nuanced difference. Most people prefer to say tensor product, but sometimes I'll lean towards a Kronecker product. They're almost synonymous. I'm willing to say that. I might be wrong, though. But basically, the idea is, and for this example, I like to just pick 2 qubits for the 2 bits for the input. And the reason being is that the number of basis states will explode exponentially if I'm expanding everything out. So if I said that n was 2, then what happens is we're really just saying this. Okay, ket 0 and then tensor product with the other ket 0. And the tensor product is how you combine individual qubit states, because when you are evaluating circuits with multiple qubits, you can't just treat each qubit independently. Like they're glued together, and it's like a massive quantum state you have to account for, and you glue it together using this Kronecker product or tensor product. And so what this actually looks like, I'll just write it out, is this ket here, the actual vector, looks like this, and this looks like this. So it's 1, 0, and 1, 0. And I always like to think of this tensor product as what I call lazy matrix multiplication. And the fact that this is what I always thought matrix multiplication should be, but matrix multiplication has a dot product embedded in it. So as a result, what this actually looks like is this: 1, 0, and then 1, 0. And it will look like your resulting vector should look something like this: 1, 0, 0, 0. So notice how I treated these like coefficients, and then I just copy pasted this in twice and did some straightforward multiplication here. But there's a 1 here. This is like a singular dangling qubit. And as a result, you will have to do the Kronecker product with 1, which is 0, 1. And using the steps that I just gave you for this product, you should be able to figure out what the resulting 8-entry vector, so this will be a vector with 8 entries, should look like. And in fact, this isn't even, that 1 should be a 0. So that's what your sort of initial position looks like. And one thing I want to mention, I don't know why, I guess some books kind of skimp on this, is with the Dirac-Brocket notation, if I give you something like this, like psi 1 and then psi 2, and notice I don't have any symbol in between, but they're just sitting right next to each other. This is an implied tensor product. So if you see these two kets together, that actually means this. Then you take the product. So there is an implicit tensor product that's going on here. So that's just some notation I wanted to clear up out of the way. So this is your initial configuration. But now we're going to go ahead and apply the Hadamards to everything. And this is straight from Qiskit uses this, or Wikipedia. I'm pretty sure Wikipedia takes from Qiskit. But the essential mathematical notation doesn't change too much. Now we're in the second step of the process, and representing our quantum state, it's going to look something like this: 2n plus 1. Then we have a nice big old sigma just sitting here, like x equals 0, 2 to the n minus 1 basis states. Then we have x here, and then you have ket 0 minus ket 1. So what's going on here? It's sort of a lot going on. So we're going to try and unpack this real quick. Excuse me, I'll take some water here. And once again, any questions, feel free to go ahead and put the question in chat, or unmute yourself. I mean, I'm monitoring what's going on my other monitor as well. So that being said, what's going to happen here? So this is just your normalizing factor. You always see this with the traditional Hadamard transform, which for those of you that were present at my quantum Fourier transform workshops, you would know that the Hadamard is nothing more than a 1-qubit discrete Fourier transform. The discrete Fourier transform and the quantum Fourier transform are almost identical. So that being said, if I have 2 qubits here, I just plug this in. So why is it n plus 1 instead of just 1 over the square root of 2n? It's because that plus 1 comes from this guy. It comes from this additional qubit here. And this, if we didn't have the ancillary qubit, like we didn't have this additional qubit that's starting in ket 1 and getting Hadamard applied to it, you wouldn't even see, this would be gone, and then the plus 1 would be gone. So the reason why we have a plus 1 in this is just because it's from that other qubit. And then what's going on, if we were to actually evaluate this, so assume n equals 2 qubits, so that would mean that we are going to the square root of 8, because 2 to the 3. And then our summation here goes from x equals 0 to, let's see, it's 2 to the n minus 1, so that goes to 3. Then we would have x, and then this is ket 0 minus ket 1. So if I were to actually write all of this out, square root of 8, and then, okay, this x actually goes from 0, and then you'd have ket 0 minus ket 1 plus, let's see, 1, ket 0 minus ket 1, and then dot, 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 and then this would go all the way to 3, ket 3, ket 0 minus ket 1. So this is essentially the whole thing written out. But you can use the distributive property to your advantage. So you don't actually have to evaluate this additional qubit the n number of times. You can actually leave this. Oh, whoops, that's not a very nice arc there. You can leave this on the outside and just evaluate your ket 0 plus ket 1 plus ket 2 plus ket 3. And I should mention that I keep putting integer numbers here. Most of the time, though, this will be represented in binary. And if you want to know what these actually look like, these are your basis kets. And what do I mean by basis kets? Well, given a 2-qubit state, so I'll put a psi here, and I'll say like, I don't know, 2 qubits. To represent any 2-qubit state, you're going to need 4 basis vectors. So 0, 0, beta 0, 1, plus, oh, wow, I'll just put C here. 1, 0 plus D, 1, 1. So once you have these coefficients, you can represent any 2-qubit state. And so these are sort of your unit bases. And I should mention that there isn't a requirement for alpha, beta, A, B, C, and D, which is this requirement. They should all be, if you take the absolute value or the magnitude and you square them, I should say the magnitude, that's probably a better thing to say. ABC squared and then D squared should equal 1. So all these coefficients should equal 1, and that makes a valid quantum state. Anytime you get something that's non-1, it's not really valid, although there might be a, yeah, you shouldn't consider it to be if you evaluate this and you get something other than 1, that means you're probably doing something wrong when you're running this algorithm. But I digress. This is just how you would express the Hadamard. And if you don't believe me, which is good, it's good if you don't believe me, because the trait of any good skeptic, any good mathematician, scientist is a healthy degree of skepticism. An equivalent way you could look at this is for each qubit, we are applying a Hadamard. So qubit 1 might look like this, ket 0, starting from 0, that's ket 0 plus ket 1 over the square root of 2. And then you could Kronecker product this, ket 0 plus ket 1 over square root of 2. And you could do this for your, any number of qubits. And then eventually, so these qubits would be the ket 0 qubits. This is your input qubits. So I should say this would be X. And then for Y, you only have 1 qubit, which is ket 0 minus ket 1 over the square root of 2. And then you can do the tensor product given this information, and you'll find out that you will get the exact same thing that this summation gives you. So this is a sort of a much more compact way of showing things, but to be safe, you can always write things out fully and evaluate for yourself. So that's step 1. So just to give you an idea, we are at this part of the circuit right now. We've just gone ahead and Hadamarded everything. And why exactly are we doing the Hadamard? Now that I've given you a bunch of math, why are we doing this Hadamard? Well, the thing is it takes all these inputs, right? I gave 0 for 2 qubits, you get 0, 0, 0, 1, 1, 0, or 1, 1. The Hadamard puts them into a superposition. So and I want to be very careful here. I'm trying not to say that the function is going to evaluate every single one of them simultaneously. That's not entirely true. In fact, if you look at Scott Aronson's TED Talk about what quantum computing is not, which I highly recommend, you will find out that it isn't really the case that the quantum computer is evaluating everything in one go. Rather, we are trying to set up the data in such a way that after evaluation, we can coax a desirable piece of data out of it. And that's where, in quantum mechanics or waves, you think of interference, constructive interference and destructive interference. And right now, it's not really apparent what exactly I mean by constructive and destructive. But at the very end, when I'll explain the phases of the qubits. And that phase component that gets introduced during evaluation is the secret recipe. It's the secret sauce that really makes this algorithm tick. Are there any questions so far before I keep going? I realize I've been talking for a pretty prolonged period of time. All right, cool. I think everyone's happy so far. The number of participants is staying at 7, which is great. It means I haven't lost anyone yet. So with that being said, let's go ahead and look at step 3. Oh, someone unmuted. Is there a question?
No. That was fine.
Okay, cool beans. So now we're going to do that step where we're going to evaluate this thing through U of f. And we got to remember that f of x has either 2 options, right? It can either be constant. So let's see, all outputs are 0 or 1, or it can be balanced. In which case, 1/2 of the outputs are going to be 0, and then the other half are going to be 1. And we've done that unitary transformation. So we've tucked our function away inside of this black box. And due to time constraints, I don't think I will go too much into how the black box gets implemented. But if you want to, I recommend like the Qiskit resources or some of the other research papers out there, which do a particularly nice job. Now, what happens in the evaluations, I'm going to rewrite the state that we just actually, hold on, can I copy? I've never actually copy pasted stuff here. Let me see if I can do that. No, I don't think I'm going to risk it. But basically, we applied the Hadamards and we got something that looked like this, right? So x is equal to 0 to the 2nth minus 1, ket x, and then we've got this dangling qubit here. That's 0 minus 1. So this is what we're going to feed into our unitary operator, or the function so far. And what you're going to get out of it is this. The normalizing factor doesn't change. This always has to be here, although this will change later on when we reapply the Hadamard. 2 to the n minus 1. This x, our basis vectors don't change. We're not changing, the basis or anything. But this guy does change, and it turns into this. Minus. And don't fret if it doesn't make sense why. Turns into this. Okay, so we see that nothing really happened to x, and that's right. We should expect that, because I just showed you in the earlier diagram with u of f. Let's see if I can find it here. There we go. This is sort of our unitary function. X goes in and x comes out unscathed, or looks like it comes out unscathed. In reality, there's some interesting stuff that goes on with the phases, and that the interesting stuff with the phases actually comes from our ancillary qubit. And the operation that gets applied from the ancillary qubit is you have one qubit, and then we map it to this. It's y XORed with f of x, whatever the output of f of x may be. And I want to kind of walk through how the derivation comes from. There's a very wonderful paper is published by CERN, or it's on the CERN archives. It's called Quantum Algorithms Revisited. It's written by I'll try and have it linked somewhere in the video of the recording, or maybe in a Medium article to promote thoroughness. But the basic idea here is, if we look at, so x is sort of a combination of all of our basis vectors. I'm omitting the summation symbol just for the sake of brevity. But if we apply our function, so we go ahead and apply the function here, what we're going to see actually is sort of the more verbose writing of what's going on here. Is x, and then you can think about it this way. You have ket 0 XORed with f of x minus ket 1, and then this is also has a XOR with f of x here. So you'll notice that because we're in the superposition state, it kind of, you have the equal opportunity of being evaluated. So with regards to ket 0 or ket 1. And then as a result, if I draw a truth table here, so f of x can either be 1 or 0, right? So if I do 0 XOR 0, that's still going to give me 0. And if I do 0 XOR 1, that's going to give me 1. So as a result, this term here is easily reduced to just f of x. Now, this up here, 1 XOR f of x, we have to keep it that way, because if you do 1 XOR 0, well, you're still going to get 1. That's fine. But you do 1 XOR 1, and that equals 0. So that means that f of x, it's not just equal to the result of f of x, because this stuff right here is f of x. But this stuff here is not. It's kind of flipped, if you notice. So that's why we have to do 1 XOR f of x. So if you were ever looking at the Qiskit notes and you're wondering, like, where the heck did they come up with this derivation, that is, if you just draw like a simple truth table out, you will find out that this is what actually happens. But the reality of the situation is there's another simplification that happens, and it looks something like this. Now it becomes -1 to the power of f of x times ket x times ket 0 minus ket 1. And you may raise your eyebrows at this, saying, like, wait a minute, where did this -1 of f of x come from? And this is sort of a phase factor that gets introduced by evaluating the function. This phase factor is incredibly important into why the algorithm is able to, in one go, figure out if it's balanced or constant. But if you don't believe me, which is good, I encourage that, I will go ahead and show you how we can jump from f of x and then minus 1 mod, or not mod, 1 XOR f of x to this expression here. And all it takes is a little bit of patience in terms of verbosity. So I'm going to go ahead and just, if I do -1 of f of x, and then dot, I'm just going to split it down the center, so it's a nice little truth table, and then I declare that f of x is equal to 1. So in this arena here, or not arena, and this is part of the truth table, I'm going to take this expression here and evaluate it using the fact that f of x is equal to 1. So what that means is this is given 1 minus, and then this would be 1 XOR 1. So this is sort of for all the inputs here. Whereas in this one, I'm going to use this expression up here. So I'm going to use the fact that we're now saying that -1 to the power of f of x is equivalent. And as a result, if I evaluate it, it's -1 to the 1, ket x, and then we still have our ket 0 minus ket 1. So that -1 is going to change the phase here. It's going to turn it into, let's see, -0 plus 1. So we've just changed the relative phase there. And if I were to keep evaluating using the older expression, which had the explicit modulo given, what actually happens now is this still stays 1, but this becomes 0. And if you'll notice that these two expressions are equivalent. And if I were to evaluate it with f of x equal to 0, you would still get the exact same thing. Or not the result wouldn't be the exact same as this, but the two methods of evaluation, using the -1 to the power of f of x, and using the more verbose f of x, or ket f of x minus ket 1 XOR f of x, will give you the same thing. So these are equivalent. These are equivalent ways of saying things, but it's just mathematically they've been written differently. And this is actually the more preferred method, because not only is it short, but it gets the idea across that we are introducing, there will be some kind of phase change that occurs that helps in the process of valuation. So those are our equivalent expressions. Now I want to go to our sort of very last step here, or actually I want to once again write the whole thing out, 2 to the n minus, or 2 to the n plus 1, excuse me, equals 0, and this would be 2 to the n minus 1, ket x, and then we still have, you would still have your 0 minus 1 here from the singular qubit. And then in here, we're going to go ahead and squeeze in that -1 of f of x. And this comes from evaluating. Now, because of the, at this point, this ancillary qubit doesn't do anything for us. It's not contributing anything. In fact, the only thing that the qubit was contributing is this phase factor. And you'll notice that this phase goes from that one qubit to sort of all the other qubits. So it introduces a global or relative phase. And if we go back to my quantum Fourier transform workshop, I kind of mentioned the difference between a global and relative phase. And the difference being that the relative phase, when you perform a measurement, you will be able to discern that there's a difference. But with the global phase, you can't. The global phase is sort of a byproduct of the math itself. And there's no real physical equivalent to that global phase. So going back here, this -1 of f of x gets, we're going to keep this guy, but this sort of, we can drop off. We can actually forget about it. So if I go all the way back up to the circuit diagram here, so right now we've just finished evaluating this step here. So now we're in the throes of the we're in the final part of our evaluation, and there is we're going to go ahead and apply this Hadamard again, and you notice that we're not applying any more operations to that ancillary qubit, because the phase from evaluation has been transferred onto x here, and y no longer serves us any useful purpose. So as a result, we can kind of drop it off from the math entirely. And the way we do that is we just omit this factor here. But if you have a keen eye, you will also notice that that means that our normalization factor is now off by 1. So this actually just becomes square root of 2 to the n. And x equals 0. And then we have our 2 to the n minus 1. That's just, we're iterating through our basis vectors. The -1 of f of x stays, and then it looks like ket x. Okay, cool. So this is actually what happens. So now we have this thing dangling here. But now to hold on, let me think real quick here. Okay, now what we have to do is I mentioned the final step. The final step. I think this is step 4, or I'll just say this is sort of the second to final step, because the final step is actually the measurement. The second thing we're going to do here is we're going to apply a Hadamard. Now, if you look at the math on Wikipedia and the math on Qiskit, you will find that they sort of jump the gun on the mathematical representation of performing another Hadamard. And just to remind you of what another Hadamard actually looks like, so if I were to write this out, right? So this is Hadamard n. So I'm applying a Hadamard of n dimensions onto a vector of n dimensions. It's going to look like this. It's 1 over the square root of 2n over the summation of x equals 0 to 2 to the n minus 1. And then if I go back here, it would just be x. So this is a Hadamard applied to a vector or to a bunch of qubit states. And because I'm applying a Hadamard again, so this is already like one Hadamard applied and evaluating through the function, but now I apply a Hadamard yet again, we're going to cleverly substitute this ket x with all the kind of junk here. But remember that this x isn't like the same qubit state. This actually gets relabeled as y, because this x isn't really our current qubit state. It's more the basis vectors that I'm telling you about. So the basis vectors, once again, if I'm just iterating from ket 0 to 1 all the way to 3. So this ket isn't actually encoding our quantum state. But so as a result, I can kind of relabel this as y and change the variable here to y as well. But what I'm telling you is that we plug in this kind of summation here, which represents the operation of applying yet another Hadamard. So what that really looks like, in fact, is 1 over the square root of 2n, and then we have the summation here, x equals 0 to the n minus 1, -1 of f of x, 1 over the square root of 2n. We got to play it safe. We still preserve our normalizing factor here. Then you have 2 to the n minus 1. Then y equals 0. Okay, now something weird is going to happen. Just bear with me. This guy may be very unintuitive at first glance, but it is part of the Hadamard application. Oh wow, actually, hold on. I've just made a huge mistake here. This, holy smokes, yeah, this is a very big mistake. My bad. This should actually be. I just realized. This is y, and then you would actually have a -1 here, and then x dot y. And this is not a dot product, by the way. This is a very special kind of product. But the basic idea here is, given that x is some bit string. Hold on, I think I've done a disservice here. Let me go ahead and amend my ways here. So if once again, the Hadamard to the n here on x is the equivalent of 1 over the square root of 2n, and then this should still be equal to, this should be y equals 0 instead. This should be y equals 0, and then 2 to the n minus 1, all over, let's see if I remember this, -y over y. Okay, this is what the actual applying a Hadamard does to a sequence of qubits here. And x could be any string of bits here, so it could be any length here.
Sorry to interrupt.
Yeah, go ahead.
But could you just quickly go through that last Hadamard bit again? Because I got confused when you started taking the y's, because I realized you made a mistake, but somewhere along the line I kind of lost track.
Yeah, sure thing. I think I should, let's see, I guess the fastest way to go would be to stop here. So I think all this other stuff I would forget about for now. And we just go back to, I'm not text mode, whoops. I'll go back to my cursor here. So we would just start back here again. Is it the, did you get confused at the part we dropped the qubit, or did that make sense?
Kind of. It's somewhere there. Actually, no. I like some clarity on that as well. Actually.
Yeah, sure thing. So if we go all the way back up here, so this is sort of the beginning state when we apply the two Hadamards. And the reason, this is because one of the qubits was in ket 1, but all the other n qubits are in ket 0. So you just have this kind of one dangling qubit, and then all the other qubits are accounted for through this operation here. And this is because we start in ket 0. But when we evaluate the function, so when we're going through the unitary operator, nothing happens to the input, so ket x, but something does happen to our ancillary qubit, because the way we defined that unitary operator was, what happens to y is this. It becomes y mod f of x. So we go from y, and then we do, or that's not mod, sorry, y zor f of x, y zor f of x. And this evaluation is all this stuff that I'm kind of doing down here, where like we're in a superposition, so it's 50-50, 0 or 1. So if you think about it that way, then I'm kind of evaluating two things at once in a sense. And as a result, I think in the more verbose writing that I did here, if you apply the function, x stays the same, but you either have 0 zor f of x minus 1 zor f of x in your two kets here. And I write out the whole truth table here by saying, well, wait a minute, we can simplify that expression, because we note that anything zor with 0 stays the same, but anything zor with 1 kind of flips. So as a result, the expression becomes f of x, or ket f of x minus 1 zor f of x inside a ket. And then I take another step and I say, well, actually, this whole thing boils down to -1 to the power of f of x, because f of x can either be 0 or 1, which means that the -1 either happens, it gets introduced to the phase, or it doesn't. And as a result, that we're still targeting, it'll still have an effect, or an equivalent effect on our ancillary qubit. But it can also now change the phases within x as well. Does that help, or is it still confusing? I mean, I understand if my explanation isn't clear.
I'm following it so far, so you can keep continuing, because I'm still trying to. I'm still waiting on the bigger picture, like how it all comes.
Yeah,
together. But yeah, so far I understand.
No problem, no problem. I'm glad. Yeah, sorry about the mistake here. Because I was like, wait a minute. I'm like, in the back of my head, I'm like, I know I'm missing something here. It's like, this doesn't look quite right. But let's see if we go back here. So yeah, you can ignore all this stuff here as well. This is not wholly true. Okay, but what I wanted to revisit is, if I apply a Hadamard to a sort of a ket here, and this ket is a binary string, by the way. So the state inside of this ket can't be some weird, like non 50-50 probability. It has to be sort of laying on the circumference of the sphere. So as so this is a very well defined binary string. It could be 0, 0, 1, 1, 1, dot, dot, dot. You can't have something like, oh, this is 3/4 of the way, or something like that. And so this equation here only holds up in times where it's like a very well defined 0 or 1. So it's a very well defined binary string, I should say. In fact, okay, yeah. So it's not the circumference. Sorry, that's not correct. Yet another mistake. It should either be pointing, your vector representing your quantum state should either be pointing up, or it's pointing down to represent 0 or 1, and you've tensor producted all together. And if I apply a Hadamard onto this entire bit string, you can represent it as something that looks like this. And this might be kind of confusing here, but so 1 over the square root of 2n, and then n being the number of qubits, and then y is just your normal basis vector. We're just iterating over the normal basis vectors. So 0 all the way to 3 in the case of if n is equal to 2, and then you have this -1 x dot y. And the way I want you to think about this guy is this will determine the sign between each basis ket. So whether or not it's going to be ket 0 plus ket 1 plus ket 2, or if this is going to be a negative. And that x dot y is not multiplication. In fact, it's a kind of binary multiplication here with a modulo kind of squeezed in. And the way it looks is, let's imagine that x in this instance is 1, 1, and we're iterating using the summation here. So what's going to happen is, so if I give it 1 over the square root of 2 to the 2, so this would just be 4, so this would be 1/2, and then I just write out the whole thing that's going on in here. So this would be -1, and then x is always going to be a 1, 1, but y, because we're iterating through it, is going to be 0, 0, and then -1, and then you would have ket 0, 0 here. So these two are the same thing. and then plus, then you'd have negative 1, 1, 1 dot 0, 1, because we're incrementing by ones. And the thing, this operation here looks more like this. So if I take the first bit and the first bit and I multiply them, then I take the XOR of them, and then I take the second bit here and the second bit here, and then I XOR them. And then as a result, this will become, 1 times 0 is 0, XOR 1. So this becomes 1. And as a result, I keep. That means the negative 1 gets introduced into the sort of relative phases that are going on with each sort of basis component. So this exponent here is kind of telling the Hadamard, like, hey, should I flip the sign or should I keep it positive? So that's what it's doing here. And by using this property, we can actually write out the whole thing, the whole Deutsch-Jozsa expression when you get to the very end, which looks something like this. So now I can write the whole thing out in all of its proper glory. And once again, thank you for bearing with me in that little mistake that I made. I know I had to kind of retrace my steps there. One f of x, and then so this would be from the original operation through the unitary function. So see, the exponent here is f of x. But now, by applying the Hadamard yet again, so we're kind of undoing what we just did earlier. Whoops. Negative 1 x dot y. I say dot. I'm sure there's like a different or a more rigorous name for it. This is equal to y equals 0 and 2 to the n minus 1, because the number of qubits doesn't change anywhere. And then you get something like this. So this is the end result of doing the whole Deutsch-Jozsa operation. In fact, we if you shuffle your terms around, you see you have like a constant and a constant, and you can actually nest these summations. So then it just becomes 1 over 2 to the n. You have your double summations going on here with, let's see, we can flip things around. So y equals 0, 2 to the n minus 1, 2 to the n minus 1, and then over x equals 0. And then I put the square brackets to emphasize you should do the inside first. Becomes negative 1 to the f of x times negative 1 x dot y, and then ket y. So this is the end result that you see on Wikipedia and the Qiskit and all the other resources, and that's how you would get this derivation. Like the real thing I wanted you guys to understand is that performing a Hadamard on n number of qubits that are in a very well-defined bit string, by the way, gives you this expression, and we kind of substituted it in for the original ket that we saw earlier, which gives us this expression here. Now, if you perform the measurement in the measurement operation, do I have it written down here? Okay, yeah, here we go. So the measurement operation is we just take all that kind of gunk up there, or in reality, I think some of it drops out. And then you would be left with something like negative 1 f of x, or this might be y. In fact, it should be y. I'm pretty confident it should be y. And then, so then you would perform a measurement on all your state, and you're trying to measure the probability that you're going to be in this state. So you're going to get all ket zeros. Now, if the function is constant, the chance of getting all your ket zeros is going to be 1. So you're going to get like a 100% chance that it's all going to be in that state. But if you get a function that is balanced, then your chances of getting that state are going to be 0, of getting all zeros. And this has to do with the constructive and destructive interference. And I'm taking this verbatim from the Qiskit textbook, in fact, because it gives like a much better explanation than I can think of right now. But if the function is constant, so if f of x is constant, when you have your input state of vectors, either no phase gets introduced, no relative phase gets introduced to the qubits. So when you perform the Hadamard, you're just going to get the same thing back. In which case, then it's all 0, because remember we started this. This is actually equivalent to. Hold on, I should say this is actually equivalent to your ket 0 to some n number of ket zeros, and there the function is constant. And by constant, I mean, so for all inputs, f of x equals 0, in which case the negative 1 to f of x in that summation just becomes 1, which means that nothing happened. You didn't introduce any phase change. So as a result, you perform the Hadamard, and the Hadamard undoes itself. So as a result, this just stays ket 0 to the end. So your chance of measuring ket 0 to the sort of tensor product at n times is going to be 1. You have a 100% chance. Now, if f of x was equal to 1, you do introduce a phase, but it's a global phase. So as a result, you perform the Hadamard, you are still going to end up with ket 0 to the n in your measurements. So it's a kind of the what they would there is a nicer math way of showing this. Unfortunately, I wasn't able to nab it in time, but it will show you that the phases here contribute to a kind of constructive interference where you set up the superposition and then your end result kind of collapses onto ket 0 for all of them. Whereas if f of x is balanced, there's a number of relative, oh, sorry, that's a bit nauseating. There's a relative phase factor that gets introduced, and that phase factor is destructive. And as a result, you don't measure ket 0, you're going to measure something else, in which case now you know that the function is balanced instead of constant. So that's sort of the secret sauce there. So that -1 f of x here is talking about introducing relative or global phases. And that in turn, by applying your Hadamards in a strategic fashion, is what is able to help the function, or is what is able to help you determine in one evaluation if the function is a balanced or constant function. Now, one last thing before I take questions, and you guys are free to go, because I do realize I'm going over time here, is if we go back to how I drew, here we go, our unitary function. There is something that can happen, and it's known as phase kickback. So why is it that despite the fact that we're doing something to this qubit, how does it bleed over to the rest of x? And when we apply the Hadamard, that's how we get the relative or global phases. There is a property in quantum computing, and a lot of circuits take advantage of this. In fact, I think literally every algorithm you can think of takes advantage of this, and it's known as phase kickback, where you can have a certain arrangement of gates. And usually it's a C0 with like a Hadamard in x, and that's the example from Qiskit, which is very nice, by the way. And the idea is you have your qubits going in. This qubit may have some kind of phase. I just call it P1. And this qubit may have another phase, P2. And if you set up your circuit just right, the phase on P2 gets kicked. It changes the phase of P1. So as a result, this phase may stay the same. But now you're able to infer what this original phase was. And by getting that phase to sort of kick back, you're able to tell what exactly, if f of x is balanced or if it's constant, that phase kickback. But if f of x is a constant, you won't see this kind of kickback happening, because it's either going to be no global phase or a global phase. And with the global phase, you don't detect anything. It doesn't change the result of your measurement. So therein lies the constructive and destructive interference. But yeah, this phase kickback does play a huge role. And unfortunately, due to the time constraints, I won't give a demo here. But the Qiskit textbook does give a wonderful example of the math, like why phase kickback happens, where given like a C0 and a number of well-chosen singular qubit operations, you can have a phase on your target qubit get kicked up to the controlled qubit, in which case you kind of extract some information from that target qubit without modifying the state of the target qubit. But that's all I have for one. Okay, this is the very last thing I want to mention. Deutsch-Jozsa isn't the only black box algorithm. There are two others: Simon's algorithm and the Bernstein-Vazirani algorithm. I just call it BV for short. And they both deal with kind of these black boxes, but they have different things they want to get out of a black box. With Bernstein-Vazirani, there's a hidden bit string, that you want to extract out of it. And Simon's algorithm has to do with the circuit for Simon's actually looks identical to the one for Deutsch-Jozsa, but the difference being that we don't put a Hadamard here, and we don't start off in ket 1. In fact, it's all ket 0. But Simon's is trying to solve for a different thing, and but the principle behind these are all the same. They're proofs that quantum computers have this promised speed up that is so heavily sought after. And I see that Jithan has put the paper in the chat, which is awesome. I definitely have to check it out, because I'm not too familiar with this idea of recursive qubits. All that being said, the floor is open to questions, so you're more than welcome to go ahead and ask away. I genuinely hope today's lesson has been of use.
why is this useful? Like, why should I care about black box algorithms, Deutsch-Jozsa, Bernstein-Vazirani, Simons? These all sound like just crazy, weird things.
Is it Vazirani or Vazirani? I always get those like
Vazirani, after Umesh Vazirani at,
Vazirani. Okay.
Berkeley. Yeah.
Ah, yes, Berkeley, another institution. Yes, Vazirani.
Okay, but yes, why are black box algorithms important?
So that's excellent. So besides the proof of a performance boost, one of the other things is, especially in Grover's algorithm, you will want to use a black box to represent some kind of function. And Grover's algorithm is a kind of search algorithm. And the idea is that Grover's will provide a speed up in terms of, like, if I give you the output of a function. Oh, wow, excuse me. Terribly sorry about that. Grover's will be able to give you that kind of speed up. So remember how we're mainly concerned with query efficiency. How many times do I have to poke or prod the black box to get an answer that I want, or some valuable piece of information without knowing what's inside that black box? So a lot of quantum algorithms use the same idea of querying a black box, or it could just be a box. They can actually know what's inside the box, but you still want the query efficiency. And the idea of using these Hadamards to perform superpositions and this kind of constructive and destructive interference, which helps you sift out the one particular answer you want, is almost universal across a lot of the more advanced algorithms. Is that a good explanation, Samarth? Tom says, oh, go ahead. Go ahead. Sorry.
Oh, sorry. Tom came before me. Let him go first.
Yeah, Tom says, so I'm glad that the explanation is somewhat helpful. Yeah, do read the Qiskit textbook. Although be aware, the way Qiskit orders the bits, the least significant bit and the most significant bit is flipped. And I think they have like a good argument for it, which I quite frankly am not the biggest fan of, but that's my personal taste. And I feel, this will be uploaded to YouTube. So Tom, feel free to revisit this because there are a lot of missing steps in the Qiskit explanation that were my motivation for giving this workshop, was to fill in those missing steps. Like, how do you jump from 1 sigma to like the double summation going on? That's what I was trying to do. So yeah, and I should hopefully have this on YouTube soon. Pardon the gaping error here, but yeah, but I'm glad to hear it's useful. Jithan, why don't you go ahead and ask your question?
So it's a bit of a two-part question, because you mentioned a lot of phase transitions throughout the equation, and there's a global phase as well. Am I right so far?
Yeah, that's you're on
Yeah.
you're on par.
So my question is this: one, when you mention a black box, how exactly do you define it? Is it like absolutely unknowable, or are there aspects to it that parameters that you put to that definition within this context? I mean, within this explanation.
Excellent.
And the second part to that question is, as far as the phase transitions are concerned, are they static or are they dynamic? Do you assume this to just be like a completely static sort of equation as far as the phase transitions are concerned?
I'll answer the black box first. Samarth, do you have anything on static and dynamic phases? I'm not too familiar with this entry here.
Yeah, I mean, like looking at the paper that you sent, and yeah, like that question, like there are quantum computing models wherein you can have those things, particularly photonic quantum computers, because you can get like some sort of a changing phase, and you can get some sort of continuous variability. But yeah, for the superconducting quantum bits, which is I think what most of the circuit-based diagrams and whatnot are kind of focused on. That's something that I like is tougher to have, and they, like, for the most part, don't have it. I think there's like one company called Q Control that like is looking at, you know, how you can maybe modulate the noise within the quantum computing device, or at least control those pulses a bit more, so you can get like some of these more dynamic phases or some sort of form of recursion. But yeah, as standard, like these devices, the superconducting devices just don't don't have that as a functionality, and these would be considered as a static phases, in that, you know, like your black box, so to say, would be like, you know, a translation, or your Hadamard, for example, would be a translation of you know, a certain phase frequency, right? And it wouldn't be changing over time. It would just be like that phase frequency takes place, and then your wave is changed by that much, but nothing. But it's not like that will continue to change, right? Based on anything. But yeah, I guess you want to explain the black box part.
Yeah, sure thing. I mean, I'm not too familiar with the static or dynamic phases. So what is black box? In this example, like Deutsch-Jozsa, the assumption is like, oh, you don't know what's on the inside. And by the definitions I'm giving here are not like official, or like, this is just in my head what I consider. I mean, it's probably better to just call it a box. It's just like a nice way to compartmentalize your function. Although the algorithm's kind of proof of concept is that, okay, you don't know how the function operates. Or better yet, the idea is that you shouldn't have to worry about how the function operates. You should only have to worry about how you prepare your inputs and how you process the outputs. So that's, your main concern is more like the inputs, and then your black box. You usually don't have to worry about how the black box operates for the algorithm to work, and then input and then your output. You do some post processing, like the other, like applying a Hadamard a second time to detect the changes in relative or global phase, and then you have your measurement here.
Well, I mean, I wouldn't necessarily just like say it's like a black box in the same way as, like, you know, companies describe their products as black boxes. Like yesterday, I was watching a documentary about Enron, and Enron described their financial model as a black box that nobody understood how it worked
For
and how
good
they're
reason.
making money, right?
For
This is
good
not
reason.
a black box in that sense. You know what the gate in the middle does, right? I mean, you had it earlier. It's a unitary gate that has a certain phase, and it's after the Hadamards. It's more like, you know, with a lot of these quantum algorithms, why they call it black boxes, they don't know exactly like why it produces that result. Like how come the combination of these Hadamards with this unitary gate produces this kind of a result that can be actually useful for solving some certain problems. So that's where the black box comes from, not the actual functionality itself. Yeah, you know exactly, like, yeah, you know, these are all the pulses that the chip will be hit with, right? I mean, it's you know exactly what's going to happen. It's not like you don't know what's going to happen on the chip itself.
Right. I think like for the purposes of the algorithm, though, like you can usually, it's just a way to like get the implementation, so you don't have to like try and divert your attention away from worrying about how exactly the black box is implemented. It's as Samarth said, like the concern is more on I would say, like, getting your inputs and outputs processed right, and therein lies kind of your so it is admittedly a kind of a loose definition, at least from my knowledge, but yeah, that's I hope that's a satisfactory answer.
Yeah, that's that kind of explains it, but I still have my doubts on the definition of that black box. Just because it also doesn't quite, because you're using Hadamards on both sides. It's not obvious to me that the entire process is non-symmetrical. Does that make sense?
Non-symmetrical. So
because the way you're approaching it now, you have like the qubits go in, you have the Hadamards affected before it goes into the black box, Then you verify it with another set of Hadamard's before you post-process, and you get the answer. Am I right so far?
Right, right. So yeah, we have this kind of transformation going on here. Yep.
So because, and this is why the whole definition of the black box confuses me, because what it could go both ways in that case if the definition of the inputs and outputs, given that, in relation to how you define that black box, could be symmetrical, basically.
I think the black box, I mean, it is symmetrical in the sense that if I gave you the outputs of the black box and you fed it through the black box, you'd get your original, like there is a sense of reversibility. I think that's what.
Yeah, basically, yeah. That's part of my doubt, because it seems linear, but it's not obvious, if that makes sense.
Yes, I think I see where your concern is.
And it's all due to the fact that you consider the algorithm as a black box. It's not, and again, this goes.
Well, I mean, I think we should clarify. The algorithm isn't a black. It's just the thing that the algorithm is evaluating. I mean, you convert it into the the kind of unitary, because we started out with a function that is not symmetric. It's very much asymmetric, and we turned it into this kind of symmetric thing that for our purposes is useful for figuring out if it's balanced or constant.
Oh, okay. So it's more of a practical outcome than. Okay.
Yeah, no, that's exactly it. I mean, yeah, I mean, the reason I think of like why they might like to use the word black box is just like the principle is that if you change what's inside the black box, the algorithm shouldn't have to be completely, rephrased for a different black box. I mean, like, yes, the implementation of the black box will change because you have a different function, and Qiskit, once again shows you can use a bunch of C naughts to represent the logic, but the algorithm itself, so all this stuff here with the Hadamards and the reverse Hadamard and the measurement, that will stay the same regardless of the box, as well as the number of bits, because I put n here. So if this could scale up to 64 or 1,000 or 1,000,000 bits of input, and it should remain feasible. Like the performance shouldn't degrade, and the principle of operation will stay preserved. So that's how I think of black boxes. Like you shouldn't. Any change to this box should not break the entire algorithm.
Fair enough.
But also, historically, I mean, the term black box though is like we used to introduce the idea of a function, right? So if I give you some input, say the number 0, and there's a black box is literally how you would think of f of x, because this is writing f of x is a lot easier than writing the whole function that I might be using, like x squared, 2 to the x cubed plus the floor of 3 over 2 to the x. But you shouldn't have to worry about the internals too much to be able to perform the actual algorithm. So it's sort of a convenient sort of universal representation of whatever function you may have is how I would think of it.
Sweet.
Yeah, sorry, sorry it took a bit to explain that.
No, I kind of get it, because I just recall some similar equations in acoustics that deal with something similar to this. Where,
okay.
Anyway, so but thanks for that explanation. That clarified me. It gave me some clarity.
Well, I'm glad. I mean, the one thing I don't want to do is make anything any more confusing. Otherwise, it defeats the purpose of hosting these workshops.
Fair enough.
That being said, and if there are any, I'll give like another 1 or 2 minutes for any more questions, and then you guys are free to go. I know I've definitely gone way over time once again, but these algorithms always have a number of nuances that you should definitely pay attention to, and a lot of papers love to skip steps, which I hate, but that might just be because I'm not as mathematically inclined as many others, which is why I like to take the time to break things down and be able to share that with people who may also have a similar level of experience.
I just wanted to add, like, this is why, you know, in a lot of ways, like a lot of researchers in this space are unhappy with the quantum devices that exist today. And conversely, the quantum devices that exist today and quantum algorithms that exist today could still be really useful because of the fact that, like, this kind of treatment of quantum algorithms and you know, writing of quantum circuits without really considering necessarily the exact hardware usage and like how exactly it's going to deal with that application, and just writing in terms of the set of gates is what quantum physicists and yeah, quantum theorists would ideally love to see. And that's not necessarily like completely possible yet in terms of, like, you know, doing it at scale with, you know, a few tens or hundreds of qubits. But then at the same time, you know, you have folks who are like combining quantum bits with like machine learning, and they're using quantum bits for random number generation and, you know, a bunch of different stuff. So it's definitely not useless. It may still not be like that much better than doing something on a supercomputer, but it's definitely better than a classical device, like a traditional, like normal computer, classical device. So yeah, it's definitely like, that's definitely something I think all of us should take into account, is what is the type of hardware we're using, and how much, what are the kind of you know, noises and abilities it has, because that will also change things a lot, and it's still very much so the early days in terms of hardware still. Like, and but most of this code is really just assembly code for this device, right? None of it's like, you know, any better. And yeah, just thought I would mention that.
Yeah, I mean, Smarth isn't wrong about the assembly code. I mean, where we are with quantum computers, it's literally very much assembly level. Although I'm certain, you know, as time progresses, we'll definitely see more universal languages. All right. Well, that being said, I'll go ahead and stop the recording now.